Hi friends, today we have a class on heaps. It's a very popular data structure and has wide range of applications. Just a brief introduction about myself. I am Arpit Gupta. I am a software engineer, programming mostly in Java and C++, and I am staying in Noida, India. Right. So let's get to the topic. So today we have the topic binary heaps. A heap can also be a heap like an n-ary heap, but today what we are going to discuss is mostly binary heaps. And when I say heap, it actually means a binary heap. Okay, right. So right, let us see what a binary heap can be represented as. Now before we come to binary heaps, it's important to understand what's a complete binary tree or an almost complete binary tree, which we also call as ACBT. A complete binary tree or a almost complete binary tree, these two terms are sometimes presented as the same in certain books. For some books, almost complete binary tree is a very strict definition. So therefore, I'm going to stick with this particular term, almost complete binary tree. You see, if you have a tree, then let us say that it has a node, this, and it has two child nodes, right? Now, if we were to number the nodes in such a manner that if a node is represented by the number x, then the left child would be 2 into x and the right child will be 2 into x plus 1. So if we follow this convention for storing the nodes of a tree in an array, then an ACBT is a tree where there is no space left blank in an array till the time the number n is reached. N is the total capacity of the heap or the ACBT that we're talking about. So you see, if you consider this particular tree, it is numbered like 1 2 3 1 2 3 4 5 6 7. Okay, so there is no space left blank. If you see the second tree, this node is missing, this node is missing, 1 2 3 4 5 is missing, therefore it does not follow the ACBT property. Now this one, if you see, you might say that 1 2 3 4 5 6 and 7 are missing, but you see the capacity of this, the size of this tree itself is 5. So up till 5 number there is no node which is missing. If suppose this node were not there, let's say this one not there, then it would not be an ACBT. But if you go strictly in an increasing order, 1 2 3 4 5 6 7 we are not considering because the size of the tree itself is 5. So that's why it follows the ACBT property. So the essential important thing to understand is that an ACBT can be represented by an array without wasting storage. So here we have the example. This particular tree, it has 5 elements. It has actually 6 elements. Now let us go back one more step. I said that the tree left child is represented by 2x and right child represented by 2x plus 1. This is for 1 based indexing. When you are programming in Java or C++, generally we use a 0 based indexing. So the left child will be 2p plus 1, where p is the parent. So parent will be there, its left child will be 2p plus 1, its index will be 2p plus 1. and the right child index will be 2p plus 2. Okay. So this particular tree has the size 6 and the numbers from 0 to 5 are the indices, and you see that from 0 to 5 there is no space in between, there is no blank element. Now this is a very important property because when we talk about heaps, we have to make sure that a heap follows this ACBT property. That's why we were learning it in the beginning. There's a very technical definition of an ACBT which you will find in certain books, but I found this way of explaining how an ACBT is very useful. Simply, if you represent a tree by using an array, if there is no blank space from 0 to size of the array minus 1, then it means that it's an ACBT. Okay. Now we come to our main topic, that is heaps. What is a heap? It has a tree-like structure. It can be represented by an ACBT. Now, what is the most important property of a heap? There are two types of heaps. There's a max heap and there's a min heap. A max heap is one where the element at the top, at the root, it's the maximum among all the elements of the heap. And a min heap is one in which the top element is the minimum among all elements of the heap. Right? So in general we can say, what is the property of a max heap? The property of max heap is that for any node which is a parent node, the parent node is always greater than or equal to its left child as well as its right child. It should be, so if there is like A, B and C, then A is greater than equal to B and A is greater than equal to C. This is for a max heap. And similarly you can derive what is the meaning of a min heap. So the basic idea behind a heap is that you can use it as a priority queue. It's one of the most important application of a heap, priority queue. So what we do is that if we want the elements of a particular structure, of a particular collection to come in order, right? So what we do is we keep on extracting the top of the heap, and the heap property is maintained. So each time you extract the top of the heap, you are actually taking out the most highest, the greatest element of that heap. So suppose there is a collection of elements like this: 1, 3, 5, 7, 2, 9. So if this is represented as a heap, this collection, then the first element to pop out in case of a max heap will be 9, then 7, then 5, then 3, then 2 and then 1. This is in the case of a max heap. And this being the case, it's a very useful data structure to maintain what is called a priority queue. Another application is heap sort, and we are not going to discuss heap sort in this lecture, but maybe in a different lecture when we are covering the sorting algorithms, then we'll discuss heap sort algorithm. Heap sort algorithm is useful because it runs in the time complexity of n log n. So it's one of the most efficient sorting algorithms that exist. Right. Okay. Now this is a confusion that some people have. Does heap maintain ordered collection? Which means that is there a way to traverse the whole heap in one go in order to get an ordered collection? Like we know in a binary search tree, if we do an in-order traversal, that is left, then parent, then root, then parent, then right child. If we do a traversal in this way, then a binary search tree will yield a ordered collection. that is sorted collection. But this is not the case with a heap. So a heap is not an ordered collection. You cannot traverse the heap in any order. You cannot traverse the heap in an ON complexity to get a sorted collection of the sorted view of the collection. That is not possible. So a heap does not maintain an ordered collection. All that a heap does is it maintains the property that a parent is greater than or equal to both of these child nodes, and that's for a max heap. Right. So now we are going to cover, just we're going to see a simple example of a max heap. You can see this. Now first point to note is that it's an ACBT, which means that it has elements ranging from 0 to 9 and none of the elements is missing. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All the elements are present. There is no element which is missing. Second thing to note is, because it's a mass heap, if you consider any level, the parent is always greater than or equal to both of its children. None of the children can be greater than the parent, right? So 16 is greater than 14 and 10. 14 is greater than 8 and 7. 10 is greater than 9 and 3. 8 is greater than 2 and 4. 7 is greater than 1. It does not have a right child. 7 does not have a right child, so it's okay. And we have represented this tree structure in an array. Again, you see this is an array, but it is not sorted, right? But it's a heap, nevertheless. And for programming purposes, it is important to remember, if you are using a zero-based indexing, then the left child's index is 2p plus 1, where p is the parent index. Right child is 2p plus 2, where p is again the parent index. And in order to find the parent of a child, you can use this formula, child minus 1 divided by 2. So for example, consider this node 4. So child has the index 4. The parent will have the index 4 minus 1 divided by 2. It is 3 by 2, and if you consider the integer, then 3 by 2 is actually 1, right? So the parent of the child whose index is 4 is actually 1. So this whole thing, this is very important to remember, because whenever you're going to code the solution, then this is going to help, because a child, the index of the right child, the index of the left child, the index of the parent, these are very easy to compute, and that's why we can use an array to represent our heap without wasting storage and without using any pointers. Generally, when we have a tree, we have a left child pointer, we have a right child pointer, and optionally we can also have a parent pointer. But all this is not required in an ACBT, because it's very easy to calculate what is the index of the right child, what is the index of the left child, what is the index of a parent, right? Okay. I think it's all clear right till now. Now we come to the most important part of the lecture, which is actually understanding how we operate on a heap. What are the operations on a heap? There are two major operations on a heap, as you can guess. The first one is extracting the top of the heap. Now, extracting the top of the heap is not just looking at the value of that at the top. When we say extract, it actually means we are going to remove that element from the heap, and therefore we have to restructure the heap in such a manner, that the heap property is maintained. So extracting max value is actually, if you just want to take a look at the maximum value, it's okay. You can just take a look at the value of the array at index 0. That's simple. But suppose you want to extract, you want to remove that element, then you will have to restructure our tree in such a way that the heap property is maintained, because blanks are not allowed. And the second operation that we are going to look at is how to insert a new value into the heap. Okay. Again, I am going to reiterate the basic idea of the algorithm for both of these two operations, number 1, number 2. The basic idea is, the most fundamental things is to maintain these two things, that the ACBT property should be maintained and this thing is maintained, that the parent node is greater than or equal to the right child as well as the left child. So when we are actually, you can also think about, these algorithms are not very difficult to actually come up. You can also think of these algorithms that are mentioned in this lecture. Just you need to make sure that these two things are taken care of when you are performing these two operations. Okay. So how do we operate? So how do we come up with the operation? Number 1, that is max, extract the maximum value. Okay, now we're going to go a little slowly because this is important algorithm and we want that each one of you should understand this very, very nicely. Okay, now there's an analogy that I like to use in order to explain this algorithms. So whenever you look at the heap, like in this tree structure, consider that the ball that you see is actually a slot and the value inside that circle is actually a ball. So what you have is this. When you see this circle, it's actually a slot, and the value inside that, whatever it may be x, this is actually a ball. So there's a slot and there's a ball. Why I use this analogy is because often you'd see that we take out the ball from the slot, that is, we take out the element from that particular position, but it's not that we delete that position remains, right? So it's important to distinguish between the ball, that is the element, and the slot. Okay, right. So let us now begin. This is the initial position of our heap. We have 15 at the top and we have elements 12, 10, 7, 5, 9, 6, 3, 4. They are all following the heap property. The size of this heap is 9. That is, you have elements ranging from index 0 to index 8. Okay. Now, what we are required to do? We are required to remove this element 15, which is staying at the top of the heap. Alright, so what we are doing is, we'll remove this element, right? We remove this element and we return to the user. That's what is wanted. Now this slot is empty. What to do with this slot? Okay, so what we are going to do is something very innovative. What we are going to do is, see, you may say that this slot is empty. Now let us fill it with this. Let's suppose you might think like that now this slot is empty. Let us fill it with 12, right? Let's move like this. But why this approach does not work is because if you do like this recursively, you just take the lower of the two children and keep on moving up and up. What it will do is it may leave a blank in your heap, and it may violate the ACBT property. Therefore, we cannot do like that. So what we have done is, from the top slot we have removed 15, that is the element, and simultaneously what we have done is we are going to cut this slot from the bottom, that is slot number 8. Right now we are removing the slot itself, not just the element inside that. So removing this slot means basically that we are doing something like size minus minus. That is, we're reducing the size of the heap from 9 to 8. Now the size of the heap is going to be 8. We have removed this slot itself, and we take out the element inside it, that is 4, and we place it at the top of the heap. You see, this has become a little bit messy, so let's go back to the original structure. See this is the original heap. We have taken out 15, and we have cut this slot, and we have taken this 4, and we have made it go all the way over here. Okay, so this is what you see in this step. Just forget everything. Now this is the position. This slot is gone. We have 4 at the top. Now what is the problem? This 4, it's causing the heap to violate the max heap property, because it is smaller than both of its children. Now what we have to do is we have to find the right position for this number 4 in the heap, and its process is called a heap. And what is this called? It's called a heapify procedure. You'll find it in many books. And in heapify we are doing a shift down, because the element is at the top, and we have to make sure that it goes down and down and down until it finds its proper position in the heap. Okay, so what is the first step? Let us compare it with both the children. Now this is very important, remember. This 4, it has two children, one is 12, another is 10. You need to compare it with both the elements, and you need to come up with the largest among these 3, the parent and the 2 children. In this case, the left child is the greatest, right? So what we are going to do is we are going to swap 4 with its left child. Swap. So what you see, 4 was here, 12 was here. Now 4 is in place of its left child, and 12 has come here. We have swapped 12 and 4. Size remains the same, 8. Now let's consider this position. 4 is the parent, 7 and 5 are the children. Coincidentally, both of them are again greater than 4. Now what to do? Compare 4 with left child and the right child. 7 is the greater among the 2 children, and therefore we swap 4 with 7. This is what we have done. Swap 4 with 7. Or we can also say that swap the elements in index number 1 and index number 3. This is what we have in the next step. Now consider this position. Now 4, where it is sitting, it has no right child. There is no right child, and it has a left child whose value is 3, which is actually less than the parent. So we are done here. We don't need to make any swap, because the parent is greater than the children, the only children that it has. And so we just stop at that. So that's the whole point. We do not need to do the whole process till the leaf node. We can stop at whatever place our anonymous, what we are called as anonymous element. This was our anonymous element. It's number 4. Once it has found space in the heap, we don't need to do the recur. We don't need to, keep on going to the last node. This is it. Just stop here. Don't need to go any further. I think it's pretty clear. Let us, okay, this is all messed up. So the whole idea is we go from the top, we insert the last element, we cut the last element and we put it at the top, and then we let the element that is at the top sift down so that it find its proper position in the heap, so that the heap property is not violated. That's it. And this operation can be performed in log n to the base 2. So for example, if you have a heap of size n equal to 1000, then how many operations are required to get the element at the top to its proper position? It's actually log to the base 2 of 1000, which is roughly equal to 10. Okay. Now we are going to come to the second operation of a heap, which is inserting a value in the heap. It's also similar to the previous one with a little bit of difference. In the extracting the max value, that operation, we were actually doing a sift down. We were letting the maximum, we were letting our elements value flow down the heap. In this operation, when we are doing insertion in the heap, we are actually going to do a sift up. Let us see what it means. So initially we have a heap of size 8, numbers ranging from, index ranging from 0 to 7, and we are required to insert this element 15 in the heap. Okay. Now the heap becomes of size 9, size plus plus. Earlier it was 8, now it becomes 9. Now see, in this diagram I have used the red marker, so you will see that position of our element, new element that we have inserted in red. So we have created a new slot. Now this is a new slot, slot number 8 for this element 15. Okay, and now we are going to make sure that this 15 find its correct position in the heap. Now we consider this triplet. The most best part about this particular operation is that you don't need to consider the other child. So for example, I am at this place 15. I need to only deal with my parent. I don't need to deal with the other child. Okay, we don't need to consider this. This is not required. So just compare 15 with the parent 4. 15 is greater, swap. 15 comes to this position. Now again compare 15 with its parent, which value is 7. 15 is greater than 7, therefore swap. Now again at this position, compare it with its parent, 15 and 12, 15 is greater, swap. Now 15 is at the top of the heap. There is no further place to go, so just stop. Now it could also have been that, let us say that instead of 15, our element that we wanted to insert was value, let's say its value was 11. Okay, so let us say if it was 11, then what would have happened? Then this value would be 11 here, right? Now 11 and 12, whose value is greater? 12 is greater, so there is no need to swap. So in that case, if our element to be inserted were 11 instead of 15, then we can say that our operation would have stopped at step number 3 only. We don't need to go to step number 4. We don't need to place our code in a loop until the top of the heap is reached, because at this point itself it has achieved its rightful position in the heap. It is greater than its two children and it is smaller than its parent. That's all we want. Okay, but coming back to the original example, 15 was the number that we considered, so it has reached the top of the heap, right? And that's it. Right, so one observation is that if you see this original heap, this heap is actually, what is the height of this heap? The height of this heap is 3, and therefore the number of operations that are required to insert a new element in the heap is actually nothing but 3, and the height is basically nothing but the log to the base 2 of n, where n is the size of the heap. Again, we have achieved the operation in log n complexity. So the deletion operation is also log n and the insertion operation is also log n. Now we are going to come to a kind of theoretical topic which is sometimes asked in different companies. It could be asked in interviews, and there's also general confusion among many people's mind. What is the difference between a heap and a binary search tree? So I have listed some of the differences here, and we can go through them one by one. A heap is an unordered collection. A binary search tree is an ordered collection. If you traverse a binary search tree in an in-order manner, then you will get an ordered collection. A heap allows duplicate values. A binary search tree does not allow a duplicate value. Insertion is O log n in both the cases, but here is the thing with a heap. So insertion and getting the maximum element, both of these operations are log n for both a heap and a binary search tree. But when we talk about binary search tree, a binary search tree are two types, balanced and unbalanced. So for an unbalanced binary search tree, these operations, insertion and retrieving the maximum element, could actually be ON for an unbalanced binary search tree. But for a balanced binary search tree like an AVL tree or a red flag tree, the worst case complexity is also O log n for both of these operations. But we have to remember that for a binary search tree, to make it balanced, this takes some effort. So you have AVL tree or a red black tree, which are balanced versions of a binary search tree, but when you want to do it, when you want to construct those trees, it takes some effort, it takes some extra operations. So we have to keep that in mind. But for a heap, it is like a natural thing. The insertion is O log n and getting the maximum element is also O log n. And that's why for a priority queue, if you don't require a sorted collection, we always prefer a heap than a binary search tree. What is the complexity of building a heap and building a binary search tree? For building a heap, it is actually ON. Now this may be a little strange to hear, because if you see that inserting an element is actually inserting an element in a in a heap is actually log n. So if you want to insert n elements, you would say that it should be actually n into log n, right, for building a heap of n elements. But actually this is not the case. There is an algorithm, we'll not discuss it here, but there is an algorithm which can build a heap of size n in complexity on. Okay, maybe I'll take it up little later, but for now you can remember that there exists an algorithm which can build a heap of n elements in complexity on. Okay, for a binary search tree it is always on log n. And now the most important part, storage. So whenever you are considering a binary search tree, it has to be generally stored in a linked list form. That is, you need to have a structure like node, where you'll have a pointer to a left child, you'll have a pointer to a right child, sometimes you may even have a pointer to a parent. You need to have this kind of structure of a node, and they are connected to each other through these pointers, left child, right child, and parent. In the case of a heap, the storage is almost always an array, and this is the big advantage. It's always an array because a heap can be represented as a ACBT, or an almost complete binary tree, and that's why it can be represented in an array. Okay, so we have covered certain points, and keep this in mind. And the last part, the applications of a heap. It is used the priority queue, as we always saw. It is used in a very efficient algorithm for sorting called heap sort, and it's also used in a data compression technique which is called Huffman codes. We'll not go deeply into this topic, data compression using Huffman codes, but if we find time, then we may have a video of this again, right? So here we have covered a lot of things in this topic. We covered what's an ACBT, the representation of heap as an ACBT. We covered two operations of a heap, that is deletion, top element, and insertion. And then we finally take a look at the difference between a heap versus a binary search tree. One final note that I'd like to add is, if you want to find an element, search for an element, in a heap, what is the complexity? It's not O log n. No. If you want to search for an element in a heap, you have to go through each and element of the heap, and therefore the complexity of searching an element in a heap is actually On, and that you have to remember, because if your requirement is to search for element in a collection very quickly, then heap is not the data structure for you. For then you have to go for a binary search tree, or you have to go for hashing. In a binary search tree, the complexity for searching an element is O log n. In a heap, the complexity of searching a random element is On, right? Just keep that in mind. Okay, we have come to the end of the lecture. Thank you very much.